Imagine standing on the sidewalk and someone accidentally bumps into your shoulder. You sway for a second, catch your balance, and pop back upright. In the maritime world, that temporary tilt caused by an outside force, like a strong gust of wind or a crashing wave, is called a heel. Now, imagine slinging a massive 80-pound duffel bag over one shoulder. Your spine naturally bends to the side to handle the uneven weight, and you stay tilted for as long as you carry it. That permanent lean is called a list. Cargo ships experience these exact same physical realities. If a storm blows hard against the side of the hull, the ship heels over, but it rights itself the moment the wind dies down. If the crew loads too many heavy shipping containers on the port side, the ship develops a permanent list. The vessel is at the mercy of its own internal cargo. That off-center weight creates a constant, dangerous tilt that no calm sea or perfectly still air can fix.
The only way to cure a list is to rearrange the weight from the inside. This diagram shows a cross-section of a perfectly level ship in the water. Every floating vessel is caught in a constant tug-of-war between two invisible forces. The total weight of the ship pushes straight down through a single point, the red dot called the center of gravity. Pushing straight back up against it is the water's upward force, concentrated at the blue dot, the center of buoyancy. When a ship is perfectly upright, these two dots align perfectly on a vertical centerline. Watch what happens when we drop a massive cargo block onto the right side of the deck. The ship's total center of gravity slides horizontally off that safe centerline. Now those two dots are out of vertical alignment. Gravity is pushing down on the right, while buoyancy is pushing up on the left. This creates a rotational twisting force. The uneven pressure physically forces the ship to tilt, dipping its right side deeper into the water. As the hull pushes deeper, the underwater shape changes, causing the blue buoyancy dot to slide over. The ship will continue to lean over until that blue buoyancy dot travels far enough to sit exactly underneath the newly shifted red gravity dot. Once they are stacked vertically again, the twisting stops. A leaning ship isn't broken or defective. That alarming tilt is simply the physical geometry of the vessel finding a new balance point. It leans over to keep those opposing forces aligned, which is the exact mechanism preventing the entire massive structure from rolling entirely upside down. To keep millions of tons of steel safely balanced, marine engineers rely on the double accountant method to balance the ship's ledgers before it ever leaves the port. The first ledger is the transverse table. This calculates the exact horizontal distance that the total center of gravity has shifted left or right, away from the centerline, based on where the crew places every single container. The second ledger is the vertical table. This tracks how much weight is being loaded high up on the open deck versus deep down in the belly of the hull. This vertical table gives engineers a critical measurement known as GM, or metacentric height. GM is simply the mathematical value of the ship's top heaviness. A large GM means the bottom of the ship is heavy and stable. A small GM means the top of the ship is heavy and vulnerable. You cannot guarantee a ship's safety by solely measuring whether the left side equals the right side. You have to simultaneously calculate the vertical top heaviness to know exactly how the ship will react to the water. These two ledgers, the horizontal shift and the vertical top heaviness, combine into a single equation called the Golden Formula. This equation predicts the exact degree angle the ship will tilt. This diagram shows the geometry behind the math. The formula states that the tangent of the tilt angle, shown as theta, is equal to the horizontal shift of the gravity point divided by the vertical metacentric height, or GM. Looking at the top of the fraction, the math shows a direct relationship. If the crew shifts a massive weight horizontally toward the port or starboard side, the tilt angle grows in direct proportion. More horizontal weight means a steeper lean. But the bottom of the fraction, the vertical GM line, reveals a much more dangerous reality. Because GM is the denominator, dividing by a smaller number creates a massive result. If a ship is top-heavy, its GM is small. Under those conditions, even a tiny horizontal loading error will multiply into a severe, exaggerated tilt. The geometry proves that top-heavy vessels are exponentially more sensitive to uneven cargo. A slight miscalculation that a bottom-heavy ship would barely notice can turn into a critical rollover threat for a top-heavy one. Let's put this math to the test with a real-world crisis. A massive cargo ship is sitting in perfectly calm port waters, but it is locked into a dangerous 5-degree lean. There is no wind, which means we have a permanent list caused by uneven internal weight. The crew cannot walk around thousands of shipping containers to guess which one is out of place. They run the golden formula backward to pinpoint the hidden error. Since the officers already know their current 5-degree angle, and they know the ship's vertical stability from their ledgers, they multiply the two together. This calculation reveals the exact horizontal distance that the center of gravity has slipped off the centerline. To find out exactly how much physical force caused that slip, they multiply that horizontal distance by the total displacement weight of the ship. The result is the listing moment. This gives them the precise tonnage of downward rotational force dragging the starboard side into the water. Diagnosing a severe tilt is not a guessing game. The angle of the ship provides a precise mathematical footprint, telling the crew exactly how much destructive rotational force is operating hidden inside the hull. Once the crew knows the exact tonnage dragging them down, they can engineer an equal opposite counterforce on the high side of the deck to perfectly cancel out the lean. This schematic shows the physical fix. To figure out how much weight to move, they take the total destructive force and divide it by the physical width of the deck available to them. If they have 10 meters of deck space, the math tells them exactly how many tons of cargo they need to unstrap and shift to the opposite side. As the cranes slide that heavy cargo across the top deck, the entire ship's center of gravity shifts in unison. The red gravity line travels precisely back to the vertical center line, perfectly restacking on top of buoyancy, and the vessel levels out flat against the horizon. A modern megaship is a massive floating balancing act. The placement of every container is a calculated decision that determines whether the vessel stays upright or risks a rollover. Global logistics relies on this high-stakes daily balancing act. Before a single mooring line is untied, simple trigonometry and careful geometry stand as a crew's only true defense against millions of tons of steel capsizing into the sea. If you want to see how engineering keeps the modern world afloat, make sure to like and subscribe.